Okay, so today we're going to continue talking about the broker pattern, focusing on the implementation of broker in the context of Android, as well as talking more generally about what it means to implement broker. And we're also going to talk about another pattern called the publisher-subscriber pattern. And we'll talk about how those things are realized in Android as well. So first, let's talk about the broker. If you recall, last class, at the end of last class, we talked about the broker, and I talked about how broker is a pattern that's used to shield clients from communication mechanisms and infrastructure concerns when they talk to services implemented in servers, which typically run in processes either on the same machine or in a separate machine. And we talked about how the broker takes care of all the low-level details, things like connection management, data transfer protocols, concurrency control, synchronization, threading, some fault tolerance thrown in there, memory management, all that kind of good stuff. That low-level stuff is sort of hidden from you and encapsulated by the underlying broker mechanisms. And so we talked last time about the good and the bad about the brokers and sort of the applicability and so on. And now what we're going to do is we're going to talk about how you might implement a broker. And of course, we're going to do it in the context of Android. So one of the first things you need to do is figure out what is your invocation interface going to look like. Now, there's a couple of different ways to ask this question. One way to ask the question is, what's the client applications interface going to look like, and do you want to make it as transparent as possible from the client? So if you want transparency, you're going to want to use some broker or some proxy-like mechanisms. We're going to get to that in a second. What I'm thinking about here is a little bit lower level than that. It's what's the interface that a proxy or an application that wants to program a little closer to the metal going to use in order to pass something to the broker itself. So how does a client invoke an operation on the broker? And so basically what we're going to do is come up with a way to allow somebody, either the client or the client's proxy, to pass a message from the client over to the server. And if you take a look here, you can see the way this is done in Android is something that's actually provided for by the underlying infrastructure, and it's this transact method. And transact is used to send the data. It's something that's exposed by the binder class, which is the lower level mechanism that does communication in Android, a lower level mechanism. There's lower levels than the binder. We'll talk about in a minute. But basically, it provides a method called transact, and you call transact with the code, which is basically the method that you're calling, as well as a parcel that contains the data that you want to have sent to the server, as well as how you want the reply information to come back. And so that information plus some other flags are actually used to send the data. And when somebody calls transact, which turns out typically to be the proxy that calls it, under the hood it ends up calling the onTransact method, and that will get delivered over to the server side, and there's an onTransact method that gets called back on the stub, and that's how the data gets upcalled to the server. We'll talk about that in a second. If you take a look at the binder code in Android, if you take a look at binder.java, you'll see this implementation, and it looks more or less like what I've shown you here. The next thing you need to do is you need to select and implement the marshaller. If you recall, there were sort of 3 or 4 main things you have in the broker pattern. You've got the client, obviously. You've got a requester, which is the client-side part that invokes an operation. You have the marshaller and demarshaller, which is responsible for serializing and unserializing the messages. And then you have this thing called a dispatcher. And those are the key pieces, and that's responsible for dispatching the requests to the servant, which is what actually implements things. So the marshaller has different pieces to it, but this is typically what's handled for you by the proxy pattern. So I'm not going to talk a lot about here, because we just covered that in length in the proxy discussion. But in a nutshell, as you all know, the AIDL compiler generates the code to do the proxy operations, and it basically takes a look at the data types you defined in the AIDL interface, and then it creates the appropriate calls to the lower level Java code to marshal and demarshal things from native data types into these parcels. So as you can see here, for example, if we're using our download image stuff, then there's going to be this write string call here, which is going to go ahead and take the URL or the URI or whatnot. Oops, that should be URI. And it's going to go ahead and write that thing into the parcel, and then the parcel will be passed over as part of the invocation with the transact method on the remote binder. So So we've already covered a lot of that stuff. What we're about to cover, though, now is a little bit deeper than what we covered with proxy. Proxy kind of stops at the point where things start to get interesting. So proxy is responsible for turning a method call into a message of some kind, a parcel in Android's case. But then it has to deliver that parcel somehow. How does it get there? Well, there has to be some kind of protocol to communicate between sender and receiver. And inevitably, these protocols typically use some kind of low-level byte stream or record-oriented communication mechanism, some type of transport. There's different choices, different middleware takes. It implements brokers. Some middleware uses datagrams or connectionless communication, where you don't set up a channel or you don't set up state on sender and receiver ahead of time. You just send the data out, and you either assume it gets there, or you don't care if it gets there, or you have some kind of retransmission protocol that is used at a higher level to make it get there. That's connectionless communication. Android doesn't do that. Much more common in certain kinds of middleware, especially object-oriented or non-object-oriented remote procedure call environments, is to use connection-oriented protocols. So the classic example of a connection-oriented protocol would be something like TCP/IP, where it sets up a connection and establishes state on both the sender and receiver, and then the data begins to flow. Does anybody know why TCP/IP sets up state on the sender and receiver in the kernel of the sender and receiver protocol machines prior to starting to try to deliver the actual data? What's the reason why the state is set up? First of all, does anybody know what TCP/IP does? Can someone explain to me what TCP/IP does?
It establishes a handshake between the two endpoints.
Right, handshake is established, but what's the handshake doing? What's it getting you? Why do we need it? Or what?
Sequence numbers, acknowledgement.
Reliability?
Right, exactly. The reliability is the reason. So if both sides understand the data that will be passed, then they can keep track to see if anything got dropped along the way by keeping track of sequence numbers and acknowledgements and so on. And by exchanging that information ahead of time and sort of pre-synchronizing on the starting sequence numbers and so on, then it makes it possible to not only route the information more efficiently, but also to be able to do it reliably. So if something gets dropped, the receiver knows it was expecting it and it didn't get it, and so there's a protocol that goes back and forth to try to retransmit the data if it gets dropped. And there's a whole bunch of other things that get added to TCP/IP to make it work in a variety of different networking environments. So that gives you reliability. That's what we use for the internet. In Android, we use a little bit lower level mechanism that's implemented as part of the OS kernel by something called the binder driver. And the binder driver is more of a kind of a proprietary is the wrong word, kind of a special purpose, customized protocol designed for high performance communication between processes that run on the same machine. And under the hood, it's implemented with some low-level system calls called IOCTLs or IOCTLs, IO controls. And there's a bunch of different sort of header information that gets passed back and forth. There's certain flags that get sent. This thing called binder write and read is a flag that's passed into the IOCTL call to inform that data is being sent back and forth. There's also a struct called binder transaction data that keeps track of a bunch of fields, things like what the buffer is that contains the bytes and some other information that is used by the lower level binder driver transport to move the information back and forth. And so that's kind of what's going on under the hood. This is not something you would typically use in a networked environment. It's really intended for the relatively low latency backplane that you would find if you're running in the same device. It's sort of optimized for that kind of a world. There's a nice paper that you could read about, or a nice presentation that I have a link for here that gives a lot more information about the low-level details of how the binder driver is implemented in Android. It's actually part of the Android Linux kernel extensions. Now, the next thing I'm going to talk about here, I colored it red because it doesn't apply directly to Android, but most broker implementations are running in, or many broker implementations are actually running in a networked environment, not a standalone backplane connected by a bus environment. So if that's the case, you have to have some kind of network communication. And there's a bunch of things you need to think about in that case about the protocols you use to talk across the network, which are often TCP/IP based, and then other just mechanisms you might want to add, things like acceptors and connectors and reactors and so on. And these are things we're not going to really cover here because Android doesn't have that capability. But if you start studying networked communication and networked programming environments, things like ACE or Python's Twisted or other parts of Java like Jetty and Netty and so on, you'll find lots of examples of these kinds of patterns used as part of the network communication layers. But we're not going to really cover them right now. The next thing you have to think about if you're trying to build a broker is think through the issues related to resource management. So resource management is an important part of any system, especially as it scales, because you want to make sure that these resources that are in high demand but somewhat scarce supply are properly allocated and deallocated by something, the operating system, the middleware, or some combination. And the key point here is that you don't have an infinite amount of this stuff. What are some good examples of resources that you don't really have an infinite amount of in the context of a broker or some kind of communication system?
Ports.
Ports, great example. So ports are typically endpoints of communication that queue up data that goes to them. They're addressable somehow. And you don't have an unlimited number of ports. You'll eventually run out. Of course, why do you eventually run out of ports? What's the other resource that you only have so much of before you run out of it? Memory, right. So there's only so much memory. So you have to manage memory. You have to manage ports. Other things you typically want to manage would be connections, which are often related to ports. Threads, that's a big issue. You don't want to have, don't want to start spawning threads just endlessly because you will quickly run out of them. And if you don't run out of them, you'll run out of memory, and then you'll have all kinds of thrashing and problems like that. So there's a bunch of different patterns that people have used over time to implement effective resource management. And these are protocols, these are services, and so on. So some examples that you might want to use in the context of a broker would be things like caching and pooling, which at first glance sounds similar, but they have a little bit different purpose. So oftentimes we use caching on the client side in order to have information held open even if it's not currently being used. So a good example of a cache might be some kind of connection cache, where you might share a connection to a server, and as you allocate those connections, you might cache them on the client. So if you have multiple threads that are trying to write, they can share access to the cached connection. So that's one example of something. A pool might be something like a pool of threads, where you pre-allocate a bunch of threads, you have them running, say, on the server side, and when a request comes in, the incoming binder driver picks a thread out of the pool and gives it the work to do. So pooling and caching are really both designed in order to pre-allocate and or allocate and remain allocated resources so that things don't have to be set up and torn down from scratch every time, thereby improving overall throughput. So a good quiz question would be, what are some examples of resource management, and what do they buy you in the context of the broker pattern, or something like that? There's some publications you can see. These appeared in the POSA 3 book. You can also take a look at them on the website of the authors of the POSA 3 book to talk about pooling and caching. Another thing that you need is some kind of registration interface that's used by the dispatcher to be able to register and unregister servants. Servants, keep in mind, are the things that actually get requests dispatched to them by the underlying broker middleware. So in the context of general purpose distributed computing, people have defined things like object adapters to do this kind of stuff. In the context of Android, we have something that's called the binder. And one of the methods that the binder defines is called attach interface. And you pass into that some information about the interface, and this gets stashed away so you're able to know about it, and you can find a way to get back to it later when you need to do callbacks on it. And you can take a look. All the source code is available here. Another thing we need to be able to do if we want to implement a broker is figure out some way of being able to communicate between the client and the server so the client gets access to the servants that the server is managing and owning. So how do you communicate that information back and forth? There's lots and lots of different ways to do this. In more traditional distributed broker environments, you typically use some kind of naming service or some kind of dictionary or directory service to be able to map names to object references or something else. And that's needed because we oftentimes need to be able to look these things up more like you would search things with a Google search. You want to type in some properties, and then you get back a bunch of options, and you choose one or more of them to invoke. In the case of Android, it's a little different. It's a little bit more tightly coupled. So there's a protocol that's defined here that has a couple of parts to it. One part is the onBind factory method that's defined by the server who implements the binder object, and that is responsible for giving back to the caller, which is ultimately going to be the client, a reference, an I binder to the binder. So I binder is an interface to a binder, and you can use it to invoke operations. And you can take a look at the service interface to find out more about that. The other thing that is defined on the client side is a hook method called onServiceConnected to get this binder back from the server or the service and then stash it away someplace on the client side so it's available for being used to invoke these two-way operations or one-way operations later. So there's kind of this multi-step protocol, as you may recall, where you do a bind service that causes onBind to get called on the server. That passes you back a binder object. That binder object comes back to you through onServiceConnected, the hook method. You get that thing, and then you can use it to invoke operations. So that's how Android gets the information back to the client. And you can take a look here for more information about the service connection interface. Another thing we need is some kind of mechanism to be able to transform these request messages that are coming in from the requester into upcalls that are dispatched on a method defined by our servant. Now keep in mind, in the case of Android, the servant is basically whatever typically anonymous object subclasses anonymously from stub, and then fills in the various methods that have been defined on that stub in order to carry out the work that was described in the AIDL interface. So in this particular case, this is handled by the stub. When the generated stub comes out, it has an onTransact method, and that onTransact method will take a look at the particular code that was passed over by the transmit or the transact call, and that transact call will then end up dispatching the onTransact callback, which looks at the code, which tells it how to demarshal the various fields that are passed over in the parcel, and then that's turned into native data types in this case, which are then passed to the upcall method to the actual servant implementation. In this case, we're doing the download image method for our download interface, iDownload interface. So that just gives you a sense of how those things fit together. So that kind of illustrates all the different pieces that are involved. Client invokes a method on a proxy. Proxy turns the method into a message, calls the transact method to pass it down to the broker through the requester portion. The requester sends it across using the binder driver communication protocol, comes up on the receiver side. The dispatcher receives the request, takes a look at it, figures out who it's for using the lookup mechanisms that were defined by the registration interface we looked at, and then ultimately finds the right stub, and then invokes the operation on that stub to go ahead and call back on the servant's implementation method to get the job done. So that's kind of the steps involved. And then there's also a reverse order going the other direction if there's a reply. Something else you need to do if you want to start implementing broker is figure out whether or not you're going to support asynchrony or just simply stick with synchrony. Traditional brokers tended to only support synchronous communication because they were trying to mimic two-way procedure call interfaces. So a regular procedure call is a two-way call. So for many years, remote procedure calls were kind of two-way calls. And early versions of Corba were like that too. And if you didn't like that, you used kind of one-way calls, but that had some downsides. Later on, people began to realize this is kind of limited. We really want to support asynchrony as a first-class citizen in the type system of the broker. And so people started adding new support to that. In Corba, they have something called asynchronous method invocation, for example, and asynchronous method handling, which are used to be able to give you better support for asynchrony. Microsoft COM has something similar along those lines as well. In Android, they don't really build it in directly, but you can do it by pattern convention, where you pass a callback object to via a one-way operation on the interface, the IDL interface. That goes to the server. That callback object is stashed away somewhere and then is used later, either in the same thread or some other thread, to invoke a one-way call back to the client. So you have to decide how to do it. Android doesn't really give you a lot of sophisticated support for this, but it is possible to do it, and I find it a very useful feature. And then the last thing to think about if you're trying to implement a broker, obviously there's more stuff than this, but this is the key things to think about, is whether or not you want to try to do colocation optimizations for cases where you're invoking a method on something that's in the same address space as the caller. So if you end up having your servant in the same address space as your client, do you want to do something to match those things up? And as you can see, the generated methods called as interface actually have some checks to see whether or not the call that's coming in is actually resolvable in the same address space as the client. And if it is, it just returns back the interface directly to the caller, and you can invoke a method call and it goes straight to that thing. If it's not co-located in the same address space, then it ends up making a proxy and returning the proxy. And when the proxy is called, that does all the things a proxy does to do the marshalling of the data and then the transmission of it through the binder mechanism and the binder driver and so on over to the receiver side. Any questions about any of that? Some more information here at this link about colocation optimizations, just talking about the overall concept and showing the speedups involved. So now that we've kind of seen the broker pattern implemented in various steps and kind of walk through how Android does it under the hood, let's give some examples of some pretty cool, sophisticated uses of the broker pattern in Android itself. So this particular example uses the network settings activity. You can see here, thanks to Christoph, we have a screenshot that he managed to purloin through tortuous path to get a screenshot of what this app looks like. And basically what it does is it goes out and it searches for cellular networks like, you know, CDMA or GSM or multiple providers, which you may or may not have depending on what kind of service you have, if it's locked, unlocked, carrier provided, where you are, and so on. But basically, here's what it does. There's a activity side of this thing called network settings, and that invokes start service, and that causes the activity manager service to go ahead and start up the network query service using the activator pattern that we talked about before. And then that goes ahead and initializes that particular service. And then here's kind of the quirky part. Right after it calls start service, the network settings activity then makes a call to bind service, which is a little weird because it's kind of this Frankenstein monster that's a little bit of both worlds. It's a started service, or the network query service is both a started service, because start service was called, and a bound service, because bind service was called on it. And the basic idea, the basic reason that they did this, does anybody want to hazard a guess as to the reason why they actually did it this way? What was the reason, what was the motivation for this in Android? Yes, sir?
Bound services die when there's nobody else that's bound to it, but if you start it first, then it's a started service, so it's not going to die unless it has to. Right.
So they wanted to be able to keep this service running around even if nobody was talking to it, which is kind of funny. That kind of flies in the face of a lot of what they say in Android about not doing this, but this is sort of a systems-y service, so I guess they figured that it was okay for having it running there in the background and consuming some resources. So yeah, that's exactly right. So start service causes it to be launched, and because it was started, it won't shut itself down automatically. But they wanted to be able to make AIDL calls to it, so they used bind service in order to get back the appropriate binder mechanism. Now, there's some other things they could have done to do that, but that was the most straightforward way to do it. So that calls the onBind method, which goes ahead and grabs the binder, returns it back by the callback to onServiceConnected, and it goes ahead and onServiceConnected actually turns around and invokes a method called loadNetworksList, which is a method running in the activity. And this method turns around and calls to the mBinder object in the service, and it invokes the start network query method, which is a one-way call. And then that goes ahead and starts this lookup process where it's checking to see whether or not the underlying network service is changed or what it's doing. And this actually requires some sort of registration with low-level radio interface layer service mechanisms, which will actually deliver results back via handlers at some point down the road to the network query service. And when this stuff comes back at some point down the road, then there's another callback that takes place in the handle message callback, which is being driven by low-level stuff from the radio interface layer. It invokes a callback to invoke the onQueryComplete method, passing back the list of network providers that are out there, which are then displayed so you can see what they look like. So it's just this really interesting, totally asynchronous use of the broker pattern, illustrating activator, illustrating proxy, illustrating the broker, you know, all this stuff that we've been talking about kind of all comes together, and there's both, and it's basically using an asynchronous communication mechanism to make everything work together and not block anything. One of the most important reasons why you would use asynchrony, of course, is to avoid blocking, because that's a downside where you don't want the main thread of control to block. Okay, so to summarize the broker, you have support in Android via the binder and AIDL for broker. You have support for started services, which use the command processor pattern to do message passing. And in some sense, then broker and command processor are pattern complements. You can use them in different purposes. They sort of compete with each other. And as we talked about last quiz, you would choose one over the other depending on the circumstance in which you find yourself arising. It is your job, or the job of whoever you work with, to understand the trade-offs between these patterns. And one of the nice things you get from understanding this stuff as patterns, as opposed to just understanding them in terms of the features that Android provides, is that it gives you a bird's eye view of the trade-offs between architectural alternatives. And ironically enough, as you switch between platforms, as you switch from Android to iOS, as you switch from smartphones to clouds, or whatever you move to, you'll find that these patterns exist in almost all those different contexts. And once you understand the design alternatives and trade-offs in terms of patterns, it's a heck of a lot easier to navigate through the design space. Whereas if you understand them only as specific details of one platform, like Android, or Jetty, or Netty, or Corba, or DDS, or whatnot, then as you start moving around, you'll have to relearn everything from the details up, which takes a long time, and you may miss some of the important commonalities that exist there. Okay, any questions about the broker? So now you know more than you ever possibly wanted to know about the broker and how Android works with respect to the binder and AIDL. Again, believe it or not, we've just only scratched the surface of this very, very rich topic. So if you're really into this, if for some reason you're working for a company that has to go in and modify parts of Android in order to get its requirements met for its customers and users, you're going to have to dive down even deeper. But at least now you know kind of how things are put together, and it'll help to focus your attention on the part that matters for what you're trying to do. Okay, the next thing I'm going to talk about, and this will really be the last set of patterns on these topics unless I get really inspired and think of one more between now and Wednesday, which I probably won't. We're going to talk about something called the publisher-subscriber pattern. And we're going to describe first what the pattern is and kind of how it works, what problems it solves, and then we're going to talk about how it's implemented in the context of Android. So here's a way to think about the need for this pattern. There's a bunch of system-related status information that's kept on your behalf by Android that is often useful to applications in one way or another. For example, the Android middleware and the lower-level drivers and system services keep track of the battery levels, which is a very important thing, because if you're running low on battery, you probably want to know about it so you can be alerted and plug your phone in or switch the battery or do something like that. The issue there is, how do apps find out that the battery is low? Imagine you have the phone app, right? You could be in the middle of a phone call. Your phone app isn't busy doing anything other than, helping make sure that that call's quality is good and managing things like three-way calling or caller ID, right? The phone app really shouldn't be sitting there being tightly coupled to the battery status module, right? Well, why would the phone app need to know about the details of monitoring the battery level? That would be, if you hard-coded the phone app to know about that, you would have a very tightly coupled design that would break and be brittle as you tried to make changes. Likewise, having the app continually ask some service, are you running low on battery? Are you running low on battery? Are you running low on battery? Well, pretty soon you'll run low on battery because you spend all your time asking whether you're low on battery, right? It's like having your kids say, are we there yet? Are we there yet? Are we there yet? Because it's not making it go any faster. It's just getting it to be a lot more painful. So a polling-based model isn't really the right way to go either. So what we're going to do instead is we're going to define a way to automatically publish an intent to anybody who happens to care about the status information that Android's keeping track of, like the battery levels or other kinds of things, or service quality, like your cellular signal strength. You might have something that says your cell signal is getting weak or whatnot. Move into an open area or whatever. So whenever this information changes, you want to be able to notify interested subscribers that something has happened that they may be concerned with. So here's how this works in Android. We define these things called broadcast receivers. We've talked about them before. and they have these on-receive hook methods that get called back at the appropriate time. And you can register these things by using a variety of means. You can register them by register receiver. You can register them using things like the underlying Android manifest files, whatever you need to do. And what will happen there is that tells the underlying system, actually tells the Activity Manager service, I care about these kinds of things, so if those kinds of things occur, let me know about it. So in this case, a phone app might say something like, hey, I want to know if the battery is getting low. And then later, when the battery service, through some lower level means, connected probably to hardware, device drivers, and that may actually pull stuff periodically, when it starts to realize the battery is getting low, it will go ahead and broadcast out the battery low action as an intent, and that will inform anybody who happens to care about this that the battery is getting low. And then each of those things can do whatever they need to do in order to be able to handle this. They can pop up a dialog, or they could shut down certain system services. They could dim the screen. They might drop your call. It might change the speed at which you're downloading a file. Whatever it is that you're trying to do, different parts of the system might react to battery being reduced in different ways. And of course, battery is not the only resource that might get low, right? Memory can get low, so you may have other kinds of things to keep track of memory availability as well. Just as a quick note, this example, like many examples, have a variety of patterns involved. So we've got activators involved here. We've got brokers involved here. Typically, we've got proxies involved here. There's all kinds of other stuff taking place. But the particular pattern we're going to talk about here that does this kind of magic callback approach when something happens that you're interested in, that pattern is called the publisher-subscriber pattern. And this is a very, very, very popular pattern. It goes by different names. We'll see that in a second. So one name is publish-subscribe. But publish-subscribe is really dealing with the actions or the verbs, whereas publisher-subscriber is dealing with the nouns, the things. And most patterns are described, many patterns are described in terms of the nouns, like adapter or bridge, not the actions. Adapting, right? You don't have the adapting pattern, you have the adapter pattern. So here we call it the publisher-subscriber pattern. And the intent of this pattern is to notify event handlers, which could be subscribers or observers or broadcast receivers or whatever you want to call them, when something interesting happens based on publishers or observables or subjects or whatever you want to call these things. When somebody's state changes, when something evolves, like the battery becomes low or someone notices the battery becomes low. So when an interesting state change occurs, you want to be able to notify interested subscribers that something has taken place. There's also a gang of four pattern that's very similar, although not identical, to publisher-subscriber. That's the observer pattern. And the intent of the observer pattern is to define a one-to-many dependency between objects so that when one object changes state, all the dependents are notified and updated. So they're very similar to each other. In my mind, the observer pattern is very, very, very commonly used if you're within the single address space. You have a listener or something that gets, you have a bunch of listeners that get dispatched when something occurs. And the publisher-subscriber pattern is typically used more when you're trying to go across address spaces, although that distinction is somewhat a bit artificial. Take a look here for more information about observer. So let's talk about when you might apply the publisher-subscriber pattern. So one way or one time to apply it is when an abstraction has more than one aspect, two aspects. One of them depends on the other, right? So in our example here, we had battery voltage or battery level. That was one thing. And then we had things who depend on battery level, like the phone app or something else on the phone. So there's multiple aspects, and one depends on the other. The behavior of some services or some apps may depend on the state of the battery. Likewise, when a change occurs to one object, like to the battery level, we want to tell potentially many others. Might be 0, might be 1, might be n, where n could be very large. So we don't really necessarily know how many there are. At least the guy who is monitoring the changes doesn't know how many there are. So you may have to notify an unknown number of things. So we have to notify a number of things, and those things may need to change. And something else, just to make it interesting, not every object is always interested in every change by every other object. So there may be some need to be able to filter or winnow down the number of interested subscribers that need to be informed when some publisher decides it wants to tell people that things have happened. So those are the conditions under which you would typically apply this particular pattern. So here are some of the structure and participants. As always, this maps just beautifully onto the stuff that you find in Android. There's something called an event, which in Android is an intent. That's easy. There's something called a subscriber, which is the thing that consumes events. In Android, that's a broadcast receiver, among other stuff. There's other things besides broadcast receivers, like content observers and stuff like that. There's a way to filter so that every subscriber does not receive every event. That's done through something called intent filters. There's various ways to define those. You can define them programmatically, dynamically. You can define them statically through manifest files. It's up to you what you want to do. You have a publisher, which is used to create the events in the first place, or the intents. In Android, that's typically a service or an activity. And then finally, you have something that serves as the mediator, the traffic cop, that routes the information, the intents, the events, from the publisher to one or more subscribers if their filtering criteria is satisfied. That's what's called the event channel. And in Android, that's handled by a variety of things, the context working in conjunction with the Activity Manager service. So those are all the different pieces mapping the concepts of the pattern to the pieces of Android. And that should be helpful, because once you understand how it works in Android, pretty much every other intent system and event system has a lot of things in common. Here's a quick summary of the dynamic interactions in this pattern. It starts out by having the subscribers register with the event channel. Some systems require the publishers to register as well, but that's more optional. It's almost always the case subscribers register. And the event channel keeps track of that stuff. When the publisher detects something that's changed that it thinks others may be interested in, it then goes ahead and notifies. It publishes the event. That goes to the event channel. The event channel says, there are all these different subscribers. Let me see which ones actually care about this particular type of event. Maybe it goes to everybody. Maybe it goes to some select few. Maybe it goes to some quorum. Lots of different alternatives there. Those things get pushed along, and eventually they get delivered to the actual subscribers themselves, who will then go ahead and consume the event in one way or another. Any questions about that? Pretty conventional thing to do. You'll find this used all over the place, probably too much actually in practice. So there's a number of benefits and liabilities of using the publisher-subscriber pattern. On the good side, it allows publishers and subscribers to vary independently. You can have different, the publishers don't have to know about the subscribers don't have to know about the publishers. They just have to know about something in common, which is the event channel. You register, you get notified. You don't really have to care about that kind of stuff. Think about services that you might use or you might be aware of that work this way. Twitter is a good example. If you want to follow Lady Gaga, why you want to do this, I don't know. But if you want to follow Lady Gaga or Miley Cyrus, because you like to see a train wreck unfolding in real time, then you can subscribe to their Twitter account, and they don't really know who you are. They don't really care who you are, by the way. They just want to know that you're a fan. And so as they go about the crazy things they do in their lives and tweet about it, you'll be informed, right? So it's this sort of anonymous communication. They can, in fact, it doesn't even really have to be them. It could be their handler out there, just trying to patch over a rough spot to make it look good or whatever. So the publishers and subscribers can vary and be different. You can add any number of subscribers you may want. So you might have 1, you might have 0, you might have a gazillion. And the different subscribers may choose to treat the data in different ways. So, some people, when they get the tweet of Miley Cyrus's latest, music award thing, they may immediately rush out and watch the video. Other people may call the network to complain. Other people will, take a shot of vodka, whatever they do. The different people can react in different ways to the information that's coming out their way. And so you can customize the behavior. So those are some really powerful, positive things. And what you end up with when all is said and done by using publisher-subscriber or event-based communication of this form is you end up being able to have a loosely coupled connection between different parts of your system. So things are more evolvable, they're more customizable, they don't have to all vary in lockstep. And there's even more sophisticated things you can do here. There are some downsides, though. One of the problems you can get into is you can end up with, because the publishers and subscribers don't really know about each other, you can end up in situations where you have a storm of communication taking place that nobody really realizes they're propagating, and yet because of the aggregate effect of this, the system becomes wildly overloaded. There was a great example, if you take a look at email storm on Wikipedia. There's a bunch of examples of email storms. And there's a great example of Microsoft where they pretty much melted down the Microsoft Exchange server 15 years ago or so because people hit reply all and they didn't realize it, and everybody kept hitting reply all. The story I always like to tell about this is back in the early days of email, when I was first starting out as a grad student in the late to mid 80s, people weren't as accustomed to getting lots of unwanted email as they are today. I mean, let's face it, anybody these days who gets upset about a piece of spam is probably picking up, probably focusing on the wrong thing in life to get upset about. You get an email you weren't expecting. You don't just blow up and go ballistic. I mean, those people in Nigeria really do want to give you all that money, for God's sake, right? So the point is that we're kind of accustomed to it. Way back in the day, that wasn't the case. And so what happened was funny. You'd end up on a mailing list that maybe you didn't know you'd gotten subscribed to somehow, or you'd forgotten, or you weren't expecting to get something. And somebody would send a posting out that was a little bit off topic, or you just didn't know why you were on the mailing list. And rather than doing what you do today, where you just ignore it and delete it, instead what people would do is they would reply back to the mailing list saying, please stop sending irrelevant emails to this list. And of course that would be broadcast to everybody on the list too. And then everybody else would start chiming in, why am I getting all this email I don't want? And before you know it, every person is sending responses back to every other person. So it becomes this sort of quadratic explosion of emails, and the whole system bogs down and the internet grinds to a screeching halt, and so on. That's an example of an email storm. And that occurs because you don't really realize that you're actually broadcasting your messages to everybody. You think you're just replying to one thing, but it's actually exploding it out into multiple places. Another problem you get into, and you probably also get this with mailing lists you may be on, you end up getting a lot of stuff that you don't really care about. People just sort of send it out to, let's say you're subscribed to the Red Zone channel, and so you're going to get informed every time someone scores a touchdown. Well, maybe you only care if your team scores a touchdown, and you don't care if other teams you don't like score touchdowns. In fact, it might even irritate you to find out that certain teams are scoring lots of touchdowns. So you might want to be able to have some way of winnowing out the stuff you care about from the things that you don't care about. So if you're not careful, you can end up with lots of extra data that you don't really want. Some good examples of known uses: pub/sub middleware uses these patterns, this pattern galore. Things like web services notification, data distribution service, Java messaging service, the Corba notification service, all kinds of things in that space do this pattern. And the more sophisticated ones really go off the deep end in terms of being able to have sophisticated support for quality of service and other capabilities. And then there's smartphone event notification systems like we have in Android. So things like the intent service and the binder framework and all the other things, broadcast receivers, those are all examples of this pattern as well. So the bottom line here is that publisher-subscriber helps you avoiding hard coding dependencies between publishers and subscribers. So as things change and evolve, you have less rework to do in order to take advantage of changes that may occur in terms of numbers of stuff, what they do in response to stuff, and so on. And also, subscribers and publishers can come and go, and new types can be introduced to the system oftentimes without having to make changes to what's already there. And that's one of the powerful features of advanced pub/sub middleware. It's very change resilient in a lot of ways. And the other nice thing is you don't end up having to poll stuff. You get informed when things happen, and you don't have to sit there and repeatedly ask questions, chewing up valuable resources, including your time, without really knowing about anything until it actually happens, right? So those are basically that's basically an overview of the publisher-subscriber pattern. Any questions about the pattern in terms of what it's intending to do? All right. So let's talk now about how you would actually implement the publisher-subscriber in Android. And there's a bunch of different ways to do it, so we're just going to focus on one part. So first, let's talk about what it means to implement the pattern in the first place. So there's a bunch of steps that you need to do. One of which is you have to define or determine what the publisher-subscriber mapping is. How do publishers and subscribers interact? What's the means by which they communicate? And of course, in the context of Android, this is done via an intent. And as you all know at this point, it keeps track of various things. Optionally, it keeps track of the name of something. More likely, in the case of pub/sub-like models, it keeps track of the data. It keeps track of the action, keeps track of the extras, the category, etc. Those are things you can put into an intent data structure. And then that information will get distributed by some magic cloud-like thing to the various receivers. If you want to avoid this overhead of giving everybody everything all the time, then you need to come up with some kind of filtering mechanism to narrow people's interests in certain topics or certain parts of certain topics. So in Android, this is done by the concept of intent filters. And there's different ways to define or program, implement intent filters. You can do them dynamically by creating an intent filter and then registering it when you call register receiver. You can also use the manifest file, as we show here, to specify different things, different actions, different data, and so on. And then you will only receive that stuff that matches your filters. So it's kind of like a sieve, and only things that pass through the filter or pass through the sieve are actually delivered to the end result, to the broadcast receivers. Another thing you need to do is figure out how you're going to go ahead and define and implement the subscriber registration API. And there's a couple of pieces to this. First, you have to figure out how you're going to let applications, which in this case could be activities or services, go ahead and register broadcast receivers to get called back. And there's a couple different variants here. You can have a register receiver model where you pass in the receiver you want called back and optionally the intent filter or not. And then you can also give permissions, and you can actually, even in the second case, you can actually give a handler where you want the call to take place if you don't want it to take place on the thread of control where the broadcast receiver was originally created. So you have a lot of flexibility in Android about how you control where things are going to run. These subscriptions that you make, the registrations you make of the receivers, are typically stored in some kind of internal data structure somewhere. In the case of Android, there's a very complicated means for doing this called the Activity Manager service, which I encourage you to take a look at sometime. It's vast. It's like 16,000 lines of code or more. There's a method called register receiver in there that's non-trivial. There's even longer methods we'll look at in a second. And basically what they do is they build some kind of hash map called mRegistered receivers, which is going to keep track of who's registered for which different kinds of things. So when you call register receiver, it goes ahead and checks to see if this particular receiver is already registered for this stuff. And if so, it adds it to a linked list of things that are going to be registered. And then it goes ahead and sticks it into this hash map. So you can end up with multiple receivers registered for the same intent. And that is what's used to support this group communication, this one-to-many communication. That's the hallmark of the publisher-subscriber pattern. You can have many things be dispatched just as you can have one thing be dispatched. Then you also have to figure out how to define and implement the notification API. This is the thing that the publisher uses to notify the subscribers. And once again, there's a couple different variants. We have a way of being able to say, from an application point of view, from a publisher point of view, send out this intent to all the registered broadcast receivers or all the subscribers. And Android has a couple different variants of this, if you recall. One is called send broadcast, and that sends it out to everybody, kind of in parallel. And the other is called send ordered broadcast, which serializes the way in which the dispatching takes place. And there's a whole pile of variants of send ordered broadcast that do various kinds of things. So I recommend you take a look at the documentation for more details about that. Under the hood, in the Activity Manager service, there's a bunch of methods that handle this. There's a method called broadcast intent, which is kind of the entry point into the Activity Manager service. And it very quickly grabs a lock and calls broadcast intent locked. And broadcast intent locked is like 350 lines of code. It's very, very nasty, hard to figure out code. But what it basically does is it goes ahead and it takes the intent that's being broadcast and it looks up to see whether or not that intent has been registered for in Android manifest files. Those are the static receivers. And or registered via calls to register receiver, which is a dynamic call. And it builds up a set of receivers that are going to handle these requests. And then it goes on and does a lot more stuff, which I'm not going to talk about here in detail. But if you look at the code, you'll see basically what it tries to do is it tries to send out the registered receivers, in other words, the dynamic ones, if you're not doing an ordered broadcast, it tries to send them all out concurrently. So they all get sent. It just goes through a while loop going send, 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 send. And those things get sent to all the ones that are dynamically registered. And that's because the assumption is that those processes, those activities, those services, whatnot, are up and running, or could be up and running quickly. And so they will get delivered the messages very fast, the intents very fast. All the things that are actually registered statically by manifest files, however, are delivered one at a time, because you have to start up the activity or the service, you have to start up the process, and then deliver the thing to the broadcast receiver. And so they don't want to start up all these processes unnecessarily. They do them one at a time, because that takes more effort to do that. So it's very, very complicated code. I've read it a number of times for a variety of reasons, and it's really fascinating to figure out how it all works. OK, so that's basically an overview of how you might implement the pattern. Now let's talk about how this pattern gets applied in Android. And to do this, I decided to dive down into the implementation of this pattern in the context of the battery service and the phone app, which exist in Android 4.0. So Android 4.0 is where I got the example from here. Oddly enough, Android 4.1 has changed this example slightly, and so I couldn't show you the 4.1 version because I haven't figured out all the pieces there yet. I'm not sure whether they still do this anymore in Android 4.1, but they have to somehow. Anyway, what happens here is as the following. When the phone app starts up in part of its initialization before the onCreate method is called, it goes ahead and it creates a broadcast receiver called phone app broadcast receiver. So it makes an instance of this thing. And then in its onCreate method, it goes ahead and it creates a bunch of intent filters, one of which is for action battery low, which is an intent. And then it goes ahead and it registers that intent filter along with the phone app broadcast receiver. It takes all those things and it registers those with the Activity Manager service. So that goes inside of the register receiver callback that we looked at before. And that stashes all that stuff inside that hash map we were looking at. At some point down the road, the battery service, which is a system service, is running. And when the battery service starts up, its constructor actually does something really interesting. This is a kind of cool example of patterns connected to patterns, right? A compound pattern example here. So what it basically does is it creates something that's called a U event observer, or user event observer. And it creates this thing called an M power supply observer. And it goes ahead and it registers this observer with some low-level mechanism. This is the battery monitoring hardware or device driver, something that's lurking inside the Android device framework. And then it goes ahead and just waits for something to happen. So this is an example of using the observer pattern at the low level to wait for a notification that battery voltage is low. When the low-level driver discovers that battery is low, it calls back on the onUEvent callback method using the observer pattern. And that thing turns around and calls the update method on the battery service. And the update method calls the process values method. And the process values method creates an intent, which is the action battery low intent. And it broadcasts that to anybody who happens to care about this. And there's various things that care about this. In this particular case, for the Android 4.0, this ends up being sent to the Activity Manager service. The Activity Manager service says, aha, who cares about this? Oh, I know who cares about this. The phone app cares about this, and some other stuff may care as well. But the phone app cares about this. So it turns around and calls a method internally called perform_receive, which does a whole pile of things, and eventually goes ahead and dispatches the onReceive hook method on the phone app. And then that goes ahead and does something that informs the phone application that the battery is getting low. And it's a bunch of callbacks and very convoluted and so on. But that's basically the path to the portion of Android that's handling that kind of stuff. Any questions about that? So that's an example of the illustration of the publisher-subscriber pattern in the context of Android. And oh, lo and behold, it also uses the observer pattern at a lower level in order to be able to wait to be notified when the battery voltage lowness is detected. That notifies the battery service. The battery service turns around and does a broadcast to send the event out. So we're using these patterns, kind of combining them together, chaining patterns together in order to have this callback-driven, asynchronous, anonymous, decoupled in time and space way of being able to inform interested parties that something has occurred. And if there's nobody who cares, if you've just decided, I don't care if my battery's running low, doesn't bother me, my phone will just shut itself down automatically, then there don't need to be a subscriber here. It'll just evaporate in thin air. So nothing will happen at all. Okay, so Android implements publisher-subscriber via intents and the intents framework, and it does this to give you this nice late binding effect where you can make changes after the system is running. For example, what I just showed you here takes place after the system is launched. So we're not doing what I just described to you there. We're not doing this registration in the manifest files. Instead, we're doing it in the app. So with the phone app, when the phone app starts up, it goes ahead and it creates an intent filter that says, I want to hear about the activity for the action battery. I want to hear about the intent for the action battery low. It registers that dynamically. The battery service doesn't know about the phone app. It doesn't know about the status service. It doesn't know about anything. It just knows when it learns the battery is low, it's going to tell anybody who cares something's happened. So it's very dynamic. You can come along and make changes. The intent data in this case is sort of a passive descriptor. It's a data structure that keeps track of what has changed and is being announced in the system. So something's happened, battery's low, we tell everybody about that. That's one use of intents. There are other uses of intents as well where you say, I want you to start this activity, right? So start service. That's an example of using intent to start something to be run. The broadcast example is when something's happened and you want to inform or notify others of the occurrence of something else. And you can, in Android, you can basically pass these intent objects various ways using start broadcast and send broadcast, send ordered broadcast, send sticky broadcast. There's a bunch of different ways you can do to pass this information around. Okay. Any questions about the publisher-subscriber pattern? Any questions about the broker pattern? Again, just to kind of underscore the point, as you take a look at this stuff under the hood, you'll often find out that many patterns are used together in order to implement this kind of stuff. So, for example, you'll find brokers used in both publisher-subscriber and broker. That's pretty common in both of those things. So you can go across address spaces. In some systems, people layer publisher-subscriber on top of broker. That's one model. That's the way that Corba did it. The downside, the nice part there is you get reuse. The downside is you get extra layers of overhead. Other systems that implement publisher-subscriber do so without making a broker. They just have publisher-subscriber kind of as the native mechanism. And there's all kinds of ways you can then layer brokers on top of publisher-subscribers. So you can basically take these patterns and you can take implementations of these patterns and rearrange them in all kinds of interesting ways. In real life, these days, more and more people tend to move towards some kind of publisher-subscriber-like model because you can do an awful lot of things with it. But you have to be careful that you don't end up falling into the trap of consistency at the expense of clarity. So not everything in life requires or benefits from an anonymous group communication mechanism, although many things do. So here are some examples, right? So imagine that you want to tell all your friends you just got into, I don't know, Stanford for grad school, right? So how would you tell them that? You would go ahead and post it on your Facebook page or something like that, or you'd tweet it, right? And that would be a good example of a mass, broad communication, publisher-subscriber, you publish, lots of people find out, that's great. If you want to, I don't know, invite your parents over or invite yourself over to your parents for dinner this weekend, are you going to publish that on Facebook? Probably not, right? You're going to pick up the phone and you're going to say, hey, I'm coming home this weekend. Can I bring my laundry or whatever else you want to do? And so that's a good example of a point-to-point communication. Probably using a publisher-subscriber mechanism to tweeting to the world you're going home to see your parents this weekend, unless you're Oedipus or something like that, just isn't very notable, you know. So the point is that different things are usable in different contexts. By the way, did anybody get that? Okay, good. Although this is the value of a liberal arts education. I just want to point that out to you, right? Everybody who's only like in pure engineering, like Oedipus, what the heck is that? And why do we care if he's going to see his parents? So anyway, the point is that you want to pick and choose the mechanisms to use, and patterns give you a language to describe that. And of course, reusable software, like we find in Android and other middleware, give us a vehicle for being able to implement it and reuse it more readily. OK. So that's it for this session. Any other questions?